Hello, welcome back to this channel. My name is Dr. Arzu Chhabra. I have a PhD in organic chemistry, and I am also I am a organic chemistry tutor, and I'm also a mindset academic coach for college students who are struggling or overwhelmed just because of MCAT or because they're getting some college blues. I help you go from feeling overwhelmed, stressed out, to actually taking control of your time to feel more focused and actually to feel more excited on an everyday basis. All right, so in this video series, we are actually going over the organic chemistry chapter 3rd, which is actually the substitution reaction problems, and we'll be working on that step by step, solving every problem from the 3rd chapter of Kaplan. All right, so the first problem is, under the following conditions, 1-bromo-4-methylpentane will most probably react with, right? So now in this problem, they're really asking whether, if you can identify whether this reaction is an SN1 reaction, SN2 reaction, or both, or neither, right? So whenever we are trying to identify a reaction, how we do that is by first looking at the reactant or the starting material. And if it is a 1-degree alkyl halide, right, we do see that the carbon of that alkyl halide is actually 1 degree. So when your alkyl halide is 1 degree, that is a perfect setup for actually an SN2 reaction, right? An SN1 reaction will never actually take place at the 1-degree carbon center. We know that a sure shot method to know if it is SN2 or SN1 is that if it's 1 degree, it's SN2, right? If it is 3 degrees, it is SN1. And at the 2-degree carbon centers, we then look at other parameters to actually identify whether it is SN1 or SN2. So then this is probably pretty straightforward, except the fact that we can also look at the nucleophile over here, which is actually a strong nucleophile, right? And because it is a strong nucleophile, also favored in the SN2 reaction, this reaction will proceed via an SN2 mechanism. So that was not that hard, actually. They didn't really test you in depth in that problem, right? Because some of these problems can actually make you think about a couple of parameters before you can actually come to a conclusion that it is SN1 or SN2, right? The following molecule will be classified as following, right? So now or as having. So in this problem, you are supposed to identify whether your carbon center is primary, secondary, tertiary. And again, by definition, a primary carbon center is a carbon which actually is connected to, right? Primary is connected to 1 carbon, right? Secondary carbon center is a carbon which is connected to 2 carbons. Tertiary is the one which is connected to 3 carbon centers. Okay, primary, secondary, tertiary. Quaternary, of course, you can have a carbon just connected to 4. Okay, quaternary, so quaternary. I think that's the spelling of it. It's connected to 4 carbon centers. Right, now, so if we actually look at these carbon centers, so then this carbon right over here, I'm gonna start off there, is connected to 1, 2, 3. So this one is actually 3-degree carbon center. Same way, the one at the bottom is pretty much a replica of the top one, also 3 degrees. This one, which is actually a CH2, right? So that over there is actually what type of a carbon center do we have? So that one is connected to 1 over here and then 1 towards the right. So that carbon center is actually a secondary, right? A 2-degree carbon center, also a 2-degree carbon center. CH3 is just a 1 degree carbon center, right? Connected to only 1 carbon. this carbon over here is CH3, CH3, and CH3. So this carbon center actually then is a 1, 2, 3, right? And at 4, right? This carbon center is 1, 2, 3 because effectively these CH3s are like connectivity to like 3 carbon centers, and it's already connected to so this carbon over here. So this is actually a 4 degree or actually more like a quaternary. And what I really want to do is I want to expand out this molecule because it might look confusing for some people or for some students. So I'm just going to say CH2, CH3, and then over here I'm going to say CH2, C, okay, CH3, CH3, CH3. All right, so then this carbon center is like 1, 2, 3, 4 carbons attached to it, right? If you're able to actually expand out the molecule, it will be easier for you to see that this carbon center is quaternary, right? Okay, and then we've got, so we got this one, we got that one, all right, and then you've got CH2, 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 they all are kind of similar, and if we actually think about it, this carbon center connected to this carbon and that carbon, right, so that actually is a 2 degree carbon center. So then effectively we got 2 degree, 2 degree, 2 degree, 2 degrees, 1, 2, 3, 4, okay, and then you've got 5, 6, okay, 6 2 degree carbon centers, and then we've got 1 4 degree or quaternary, 1 primary, 2 3 degrees, right? So this is what we effectively have. So which is matching. Okay, so it says 3 methyl groups, CH3s, yes, 2 ethyl groups, 4 secondary carbons, which is secondary, 4 secondary, which is 2 degrees, which is not correct. So we've got 6 secondary, 2 tertiaries, yes, 1 quaternary, and 4 primary, yes. So C is actually the correct answer then for this problem, right? Which is a really good problem here. Actually making you expand out the molecule and just checking if you're able to understand the condensed formula of, and if you can go from condensed to bond line in a structure, and also at the same time if you can identify these different carbon atoms. All right, so SN1 reactions show first order kinetics because, okay, all right, this is very theoretical, right? Like if you, whether you just know it or you just don't know it, it's not like they're making you, it's concept based. They're not, you don't have to solve anything here. So it is a first order kinetics because the rate limiting step is the first step to occur, and that is not true. It is the first order because it only depends on one molecule, right, in the reactant. Because the rate limiting step involves one molecule, that is the answer. There is only one rate limiting step. That's incorrect because 99% of the time there will always be one rate limiting step in a multi-step reaction. The reaction involves only one molecule, which is also incorrect because the reaction does involve more than one, but the rate limiting step involves only one molecule. That's why it's SN1. However, in SN2, it's the opposite. The rate limiting involves 2 steps, okay? All right. Now, the next one, the following reaction sequence is a typical of SN1 reaction. Identify the rate limiting step. Okay, so we do know that an SN1 reaction is usually 2 steps or 3 steps. And the last step is usually just the proton transfer, which is what's happening over here. And then again, this is also theoretical based, like theory based. You have to know that the first step of the reaction, it's like, because you're not the person going into the lab, actually carrying out the reaction, actually looking at kinetics and actually identifying that, okay, this step is the slow step, right? Or when this step happens, it takes longer compared to when the second step happens, right? So the scientists have actually studied that reaction. So they already know that when this reaction happens, the first step is the slow step. So the formation of that carbocation is the slow step of the reaction. And so the step 1 is actually the slow step of the reaction. So it's you have to just know that kind of stuff, right? It's just knowledge based. You're really not even doing any analysis at this point to identify, okay, you're not like comparing 4 or 5 parameters to get to the answer. It's just like either you just know that stuff or you don't. Okay, right. Which of the following would be the best solvent for an SN2 reaction? So for the solvent preferences, we know that for an SN2 reaction proceeds the best via a polar aprotic solvent, right? But it should be polar, right? It's not like you can just go get away with having an apolar solvent. So you have to have a solvent which is polar. So this is polar protic, right? Because there's a hydrogen which is present on electronegative oxygen, sorry. So it's polar protic. This one is also polar protic because the hydrogen is actually present on electronegative atom. That is the definition. Maybe I'm going to write the definition here that a polar protic solvent is a solvent which contains electronegative, which contains hydrogen on an electronegative atom. Right, solvent which contains a hydrogen on an electronegative atom is called a polar protic solvent. If it doesn't contain a hydrogen on an electronegative atom, the hydrogen is there, but not on electronegative atom, for example, oxygen, nitrogen, fluorine, then they're polar aprotic, meaning the electronegative atoms are there, hydrogen not present on electronegative atom. But electronegative atom is present. This is a side note. Okay, so then we've got this is all, there's not even an electronegative atom, and that's why it's apolar, it's not even polar. And then this CH3 S double bond O, CH3. So this compound over here is polar aprotic, right? Okay. So, and that is the solvent. Polar aprotic solvents are preferred in an SN2 reaction, right? And if you actually really think about it, the hydrogens over here, right? They're present on carbon, not on oxygen, and that is why it's actually a polar aprotic solvent. All right, so C is the answer for that problem. Which of the following conditions listed as leaving group, nucleophile, respectively, would most favor an SN2 reaction? Which of the following, conditions listed as leaving group and nucleophile would favor an SN2 reaction? So what are a preferred leaving group for an SN2 reaction and a nucleophile for an SN2 reaction, right? So if you really think about it, then the leaving group in an SN2 reaction or even an SN1, we want the leaving group to be a really good leaving group, right? And a nucleophile. And so let's say a leaving group, we want that to be a good leaving group. And for a nucleophile, we want the nucleophile to actually be a strong, right? A strong is also sometimes called naked nucleophile, right? So if it's a naked nucleophile, so then meaning that it should have a negative charge present on it. And if it doesn't have that negative charge, then it's not a strong nucleophile, then it's called a weak nucleophile. So let's think about it. Let's look at it. For a nucleophile to be a strong, meaning it should have a negative charge. So this, and also here's the other important thing, right? Like reading the problem. So you want to have the leaving group on the left, and the corresponding the molecule on the right should actually be your nucleophile, right? So we're not really just choosing just the two randomly out of the blue. So we know tosylate is OTS negative. It's actually like the best leaving group. It's one of the really good leaving groups. And then Cn minus, also a very strong nucleophile because it has a negative charge, right? So this is a possibility. And then the other possibility is I minus Cl minus. So I minus is also a really good leaving group. Cl minus is a strong nucleophile too because of the negative charge. However, I'm going to choose tosylate and Cn minus because tosylate is a better leaving group than I minus, right? And that's why option C would most favor the SN2. Option A would second most favor the option A. All right. What would be the major product of the following reaction? Oh, this is a really good reaction, right? I think, so this is not SN1, SN2, this is more like the radical halogenation reaction, right? Because we have the light, H nu, which kind of represents light. So if the reaction is proceeding via light, then that is a radical mechanism reaction, right? It proceeds via the radical mechanism. So now then in this reaction, what we do know is that Br2 is more like, okay, and then this is like the underlying knowledge that you have to be able to answer this question. That Br2, when it forms a product, is very selective, right? I think one of the most common problems or one of the common problem that actually shows up from this chapter is why is bromination so selective, however chlorination is not so selective, right? Meaning that when bromination happens, it always forms the radical, which is a very stable radical. However, when chlorination happens, it just happens all over the place, right? Meaning every carbon is able to get the chlorine. That's more statistically, it forms products governed by statistics. However, for bromination, the products are very governed by the stability of the radical. And if we think about the stability of the radical, then we've got a carbon and a hydrogen, CH3. I am expanding out the structure under option 3, right? So this is the bromination. If I think about the radical over here, before the bromination would have happened, I would have formed a secondary radical. Secondary radicals are pretty stable, right? Over here, I would have formed 1 degree radical. Over here, 1 degree radical as well. So this molecule, okay, kind of looks like, yes, it's forming a radical at this the secondary position. That's like the maximum radical that you can get in terms of like primary, secondary, tertiary, right? That is the most substituted radical that you can get. In this problem, we cannot really generate a 3 degree radical. So then the third option is actually the correct option because bromination always forms the more stable radical. All right, and well, all of that, like why all of that is like more longer problems. They're not really in the scope of these videos where we are just like really solving the problems. If you want more in-depth explanation for certain problems, of course, mention that in the comment, and I would be very happy to explain that in depth. Okay, the treatment of S2-bromobutane with sodium hydroxide results in the production of a compound with R configuration. Nice. Well, again, they are just telling us the S is converting to an R. Again, this is knowledge-based, so you have to know that this is actually an SN2 mechanism because you cannot go from S to R. Well, you can. When we have an SN1, right, then there is a retention, but the inversion is sure shot in an SN2 reaction. So, okay. And so when the inversion happens, that is a confirmation of an SN2 reaction, right? So B is actually the answer for this problem. So what is the correct boiling point of the following compounds? And if you really think about it, hexane, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And the last option is heptane, right? So we do know that longer the carbon chain, higher will be the boiling point, rule number 1, right? So number 4 actually would have the highest boiling point, so either option B or C. Then the next is 2-methylpentane, 2,2-dimethylbutane, 2-methylpentane, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2-methyl, 1, 2, 3, 4, 5, pentane. Next is 2,2-dimethylbutane, 1, 2, 3, 4, 1, 2, 3, 4. And at the second carbon, we do have two like dimethyls, right? So then 2,2-dimethyl butane, right? So now total of 6 carbons here, total of 6 carbons here, 1, 2, 3, 4, 5, 6. But here's the thing, right? 6 carbons and 6 carbons and 7 carbons. So more number of carbons, higher is the boiling point. And then as we start to get the branching reduces the boiling point because the packing reduces. So then effectively, if you really think about it, amongst 1 and 3, 3 is actually 2,2-dimethylbutane, right? 2,2-dimethyl 1, 2, 3, 4 butane. So effectively, number 3 has more branching compared to 1, which is all hexanes. So 1 then would be the higher boiling point because branching reduces the boiling point because the packing reduces, and if they will not be able to be packed very tightly. And if they're not tightly packed, the problem would be that it'll be easier to like break the intermolecular forces from the liquid state and help them get into the gaseous state really faster, right? So effectively then C is the correct answer for problem 9. All right, then problem 10, the reaction of isobutane with an unknown halogen is catalyzed by light. So this is, again, halogenation reaction, right? So then there are 2 major products obtained. So major products are 2, which is already telling us it's not a selective reaction. And we know that bromination is a lot more selective than chlorination. And this is why then A is actually the correct answer for that problem. All right, so with that, we've come to the end of the third chapter, which is based on more substitution reactions, right? And so I will see you guys in the next video where I'll be going over the 4th chapter from Kaplan, and I think I have the 2022 series, but I think a lot of these problems are very similar or moved around. And of course, if you want my help with Orgo, and if you want tutoring or mindset help, if you're struggling, reach out to me on the details given in the description, and I will see you guys next time. Bye now.